Hello, my highly esteemed students. Welcome to today's instructional video. You can see what we have is Physics 221, and the topic we are going to talk about is relativity and inertial frame of reference. My name is Professor Godwin A. Agbo, and for you to contact me, you see my email address. The first thing we need to talk about first is let us know what we are going to go home with. At the end of this lecture or this instructional video, you'll be able to explain what is a frame of reference or the concept of frame of reference. You should also be able to know what relativity and transformation are all about. One should be able to, at the end of the lecture, also explain inertial frame of reference and then be able to write the set of space-time coordinates. And so let us begin. What is relativity? We begin by saying that relativity is the study of the relationship between observations in two different frames which are in relative motion to each other. Relative motion to each other per se, you look at the picture at the right hand side, you see the Earth. This is the Earth. Let me use my laser pointers for you to see it well. This is the Sun and this is the Earth. And of course, we know that the Earth revolves around the Sun. And so the two of them are in relative motion. So if we are making observations in the Sun and observation also on Earth, you see, we find a way of relating the observations because they are two different frames of reference. The Sun is different, is one frame of reference. The Earth is another frame of reference. So if we make observations of the same event, since these two objects are moving relative to each other, we will try to find a relationship between the observations that describes what we have measured. Now, another thing we need to talk about to describe or to explain is the transformation, which we say is the basis for comparing two observations. Is the basis for comparing two observations. So special relativity actually, therefore, deals with the effects that are observed when two objects in relative motion to each other moves at speeds. Remember, at speeds close to the speed of light. That is our emphasis. In the classical case, the speed is very, very slow or lower than the speed of light. It's not up to that, far, far, far less than the speed of light. But in relativity, when we talk about relativity, we're also referring to when bodies move with closer to the speed of light, when the velocity of a body is almost close to the speed of light. And such events we experience in nature is length contraction, time dilation, mass increase, and so on and so forth. So we begin to ask, what is frame of reference? And we define it as a frame, that has a set of rules or a system you use to understand and measure things around you. So if you look at the picture at our right-hand side, you see that there is a train or a truck, which are whatever thing you describe it, that somebody ball is on and R is on the ground. You can see the line from R to the center of the truck. So between these two persons, we are asking the question, who is moving? Is it the truck that is moving? Or is it the person who is in the truck that is moving? Or is it the person on the ground that is moving? So, and the answer to this depends on the frame of reference from which each observer is describing the motion. So, we move on. So if you are on a moving train, just as the picture on the right hand side, your frame of reference might be the inside of the train. And if you are watching the train from outside, your frame of reference should be the ground. So you can now see that it is basically the perspective we use to understand what is happening. So space and time. Event we know in nature has definite location as well as time duration. And this makes us to be speaking of space-time and not space and time separately. So we talk about space, time. So in other words, we use three-dimensional Cartesian coordinates, 3D space in Cartesian coordinate, x, y, z. And so by describing the point P, we see that the position of a point P in space is another set of x, y, z, the three coordinates. However, we have other coordinates, but for simplicity, we are using three-dimensional Cartesian coordinates. So consider a particle of mass m at a point P acted upon by a force at an instant of time t as shown in this figure. This figure, we referred it to figure 1.1, but however, to figure 1.1, this we can say is figure 1.1, and the position is here in terms of x, y, z. So we have this as our position vector r with reference to the origin here. This is the center, the origin here. So the coordinate in space, which is the spatial coordinates x, y, z of the event as measured by an observer at the origin, which is this origin. This origin you see me drawing here. Let me go back to my laser so that we'll be seeing it well. So this is the origin. So you see that the coordinates in space of the event as measured by an observer at the origin of the coordinate system are x, y, z, and t. That means x, y, z is for the space and t is for the duration, which is the time. Remember, we said that every event in nature has definite location as well as time duration. So this is an activity which I have just put up for you to just use to exercise your brain. So I'm going to give you something like maybe a few seconds for you to just put it down. I'm giving you, and my time has started moving. So after 1 minute, I will go ahead, I'll continue. Yeah, welcome back. So based on this, you can now see that this event can be described in three-dimensional space together with time. Remember, we say space, time, not space and time. So in this case, we all know Newton's second law. By this means, this will now allow us or enable us to write Newton's law of motion for this event in terms of the components x, y, z. The forces, the component of the force along x is fx, along y is fy, and along z is fz. And you know that this is the general expression for Newton's second law, F is equal to ma. Then, in terms of the position vector r, you have md squared r over dt squared, knowing that the squared r over dt squared is the acceleration. And of course, r, the position vector r, is defined as ix plus jy plus kz. Now, separating the components, for the components of f of x is equal to m d squared x over dt squared. and fy equal to md squared y over dt squared, and that of fz is equal to md squared z over dt squared. The picture you are seeing there is just giving us the expression for the definition of Newton's second law, which is force equal to mass times acceleration. And in that picture, you see that you have same force applied to this is a bullet or gun. So when you have small mass, you have large acceleration. And when you have large mass, you have small acceleration. Of course, that is obvious. So that will help us to go into what we have as an inertial frame of reference. The inertial frame of reference is nothing other than when we talk about the Newton's first law. And that Newton's first law of motion, you can see someone who is in the front of a building and a car also there, trying to illustrate inertial frame of reference. You can see an aeroplane flying, and these are the things that illustrates this inertial frame of reference. So that inertial frame of reference, it could be this first one or this second one, and we are going to say that. So that if you have an object, if an object is at rest and not under any influence of any force, that object will continue to remain at rest if it was initially at rest. So if you keep a stone on the ground, and that stone on the ground you have kept is not under any influence of a force, that stone will continue to remain there. It will continue to remain there at rest since it was initially at rest. It will not move except something else, or except an external force is applied to it so that it can shift it. Alternatively, you can say that an object in its uniform motion with constant velocity will remain in this motion if it was initially in motion. For instance, the aeroplane that you see that is flying, that aeroplane will continue to fly until a force applies to it, because it is already in motion, it is already in uniform motion. And because it's already in uniform motion, it remains in that uniform motion until a brake is applied to it, and that is when it will now come down, or it will now slow down, or change direction, or do whatever. So you can imagine the beauty of this inertial frame of reference. An object that is, which we know on ourselves, we experience it. You are sitting down, and you're already sitting down where, in that case, you are at rest. And if there's no other force influencing you, telling you to stand up, you continue to remain there at rest. So this is a very simple explanation of this inertial frame of reference. So inertial frame subjects at rest and not under influence of any force will continue to remain at rest. And objects in motion or uniform motion will continue with constant velocity will continue to remain in this motion if it was initially in motion. So activity 2 will tell you what to do. So just repeat this activity 2 just to sharpen your brain and to see what you have done, that you really understand what you have been taught. And so if there's any question, then you jot it down, and then you go back to the video. It will explain to you what the answers are. State the inertial frame of reference we have just finished now. Write it down on paper and read it aloud twice. So by writing, we are practicing, and something is getting into us. So thank you, and God bless.